Hello everyone, welcome back to online lecture series on fluid mechanics and hydraulic machines. Today we are beginning a new topic, that is viscous flow. So our first topic for today is flow of viscous fluid through a circular pipe, and then we will derive Hagen-Poiseuille's formula at the end. So let's understand first this figure. Here we are having a circular pipe in which the radius is capital R, total radius is capital R. The direction of flow is from left to right, and this is the side view of the same cylinder. For analysis purpose, we have considered a elementary volume here, which is shown by A, B, C, D. This element is of delta x length and radius r. The forces which are present for this elementary volume are two. First is pressure force and second is shear force. The pressure force on side AB is P into pi r square. Why? Because side AB is actually a circular face having radius r. So it is P into pi r square, and the force, pressure force on the right face, that is CD circular face, is P plus del P over del x into delta x into whole pi r square. Apart from that, there is a shear force which is shown over here, tau into 2 pi r delta x. Here it was necessary to put 2 pi r delta x because that is the surface area on which the shear stress is being applied. Further, we will be considering a circular ring having thickness dr and radius being r. So let's begin our analysis. So let's begin our analysis. Under the equilibrium condition, the forces in x direction, the summation of forces in x direction will be 0. So here we can say that plus P into pi r square minus of P plus del P over del x delta x into pi tau into 2 pi r delta x is equal to 0. So here we have minus del p over del x delta x into pi r square, this is delta x, is equal to tau 2 pi r delta x. This is the tau. So here we can cancel few things. One r will get cancelled, delta x will get cancelled, pi will get cancelled. So we are left with tau is equal to minus del p over del x into r by 2. That is the formula for shear stress tau. Now next we will be deriving the velocity distribution. So as we know, the standard formula for shear stress is equal to mu into du upon dy, where y is the distance of element from the outer surface of pipe. In our case, if you see carefully, then the distance of face AD from this pipe surface should be capital R minus small r. So we can say that here r minus r is equal to y. So dy is equal to minus dr. So here we can write down it as is equal to mu into du upon dr. This will be d minus sign. So that is the value of tau. Now we are in position of equating these two. So we can say del p over del r is equal to r upon 2 is equal to mu into du upon dr. So here we require to evaluate the velocity distribution. So du upon dr is equal to r upon 2 mu into del p upon del x. Here it should be x. So once we integrate this, we get u is equal to 1 upon 4 mu into del p over del x into r square plus c. So here in this figure when we can say we need to evaluate this constant of integration, so we can say that when r is equal to capital R, then u will be equal to 0, because in viscous flow velocity near the wall surface is 0. So in that way we can obtain u is equal to 1 upon 4 mu into del p over del x into r square plus c, and this will be equal to 0. So we have obtained now the value of c, which is equal to minus 1 upon 4 mu into del p over del x r square. That is the value of c. So here we can write down, this is our previous equation, so we can update this equation by putting the value of c. So here the final equation can be written over here, that is u is equal to minus 1 upon 4 mu into del p over del x into the bracket r square minus r square. So that is the final equation for velocity distribution. So here we have obtained two important things. First is shear stress distribution and second is this distribution. So we can now understand the distributions in terms of figure. So here we can see both these distributions. If you see here for shear stress, it is a linear relationship. That is, when the radius is 0, shear stress is 0, that can be seen here, and as radius increases, the value of shear stress also increases and it reaches maximum towards the outer surface. And on other hand, if we see the velocity distribution, that is over here, then it is in the parabolic form. So the velocity will be maximum when r is equal to 0, and it will reach its minimum value towards the outer periphery, that is over here, and parabolic nature can also be observed. So that is all about the shear stress distribution and velocity distribution. Now we will move forward with our next theory. Over here. Our next theory let me write down here is ratio of maximum velocity to average velocity. So that is our next theory. And if you recall, in our equation that is written at the bottom here, that u is equal to -1 upon 4 mu dp over del x capital R square minus small r square. So this will get its maximum value when this small r square is 0, that is at the center. So we can directly write down the value of u maximum is equal to -1 upon 4 mu del p over del x r square. Now regarding the average velocity, for average velocity here we have considered this small circular ring with radius r and thickness dr. So here we will be considering a circular ring with radius r and thickness So in such case the value of the flow rate or discharge will be equal to u multiplied by 2 pi r dr, and the value of u that we already know is already obtained in velocity distribution, that is minus 1 upon 4 mu, that is already written at the bottom, that is del p over del x into capital R square minus small r square into 2 pi r dr. So that is the value of dq, and the value of q can be equal to integration 0 to r dq, and I will be taking constant terms directly outside, that is minus 1 upon 4 mu into 2 pi del p over del x integration 0 to r into r square r minus r cube dr. So here we will be getting minus pi upon 2 mu into del p over del x into r square upon 2 minus r raised to 4 upon 4 0 to r. So let me continue in this remaining portion. Q1 is equal to minus pi upon 2 mu into del p over del x into here r square was there, r raised to 4 upon 2 minus r raised to 4 upon 4. So here the final answer that we are getting here is equal to minus pi upon 8 mu into del p over del x into r raised to 4. That is the value of q, and the average value of velocity. Do we have enough space? No. So let me see here. We have obtained, and previously we have done up to this. So we need to copy few content from our board. Select option. is over here, and we need to copy this content also, that is over here. Now we can use few stuff. So we will continue this part over here, that is average velocity u bar can be given as q upon area, that is pi r square. So what we will be getting here is minus pi upon 8 mu del p over del x into r raised to 4 divided by pi r square. So two things I have eliminated, and we are getting the value of u bar is equal to minus 1 upon 8 mu into del p over del x into r square. That is the value of u bar. And now if you see the value of u max, that is over here, u max to u bar, if you see the ratio of the two, here it is minus 1 upon 4 mu into del p over del x r square divided by average value is minus 1 upon 8 mu into del p over del x r square is equal to 2. So finally what we are getting, u max upon u bar is equal to 2. That is the final value. And let's copy this word into our new slides. So here we are ending this lecture here. Thank you for watching this video.